Our last conic section we have to work with is the hyperbola. And up on my computer right here, this just kind of shows you again how we get that hyperbola shape. We have our double cone here, and then we slice vertically, and that gives us a parabola at the top and at the bottom. Together, we have our hyperbola. Now ellipses, we talked about the sum of the distances to each focus was the same. Here's the deal with a hyperbola. A hyperbola, each point on this hyperbola, that long distance, d1 minus d2, is the same. So right here, d1 minus d2 is the same as all the way down here on your hyperbola. The differences in those distances is the same. And same thing if you looked at a point over here on the hyperbola, your long distance to your focus minus the short distance would be the same as any point over here also. So that leads us to, again, a decent bit of vocabulary, kind of like with ellipses. There's a lot of vocab that goes along with hyperbolas. And it just says at the top here, again, a hyperbola, the difference in the distance between the foci is constant. And again, that kind of goes back with what that animation just showed. Just like ellipses and parabolas, hyperbolas have a vertex. So we'll write out a little definition here, and then I'll label it on our diagram too. Our vertex here is the turning point. Of each branch. So I'm calling this a branch, and this is a branch. Okay? So this point right here, that turning point, is a vertex. Our turning point is our vertex. All right. The transverse axis is the axis that connects the vertices. And if you look at the word transverse, the ver here, we have, I guess we kind of see part of our word of vertex here. So transverse has the vertices. Okay, so our transverse axis would be this part, connecting the vertices. Okay, the center of our hyperbola, same thing as with ellipses. It's the center, it's the midpoint. With our hyperbolas, it's a little bit easier to tell. The center is the midpoint between the vertices. So the center of our hyperbola here is at 0, 0. And we're going to keep the center at 0, 0 for all of our hyperbolas and the ellipses. Same thing. All right, then we also have this conjugate axis and the central rectangle. These parts are different, I guess. The transverse axis kind of goes along with the major axis with the ellipses. Conjugate axis kind of goes with the minor axis. It's perpendicular to the transverse axis. So the conjugate axis, here's your transverse axis, conjugate axis is perpendicular. Conjugate axis. So central rectangle then is formed by the transverse axis and the conjugate axis. We're going to draw in the central rectangle first, and then we'll talk for a second about why that central rectangle is important. All right, so our central rectangle is formed by our transverse and conjugate axis. If you imagine where this green line and the red line would go if we formed a rectangle, Our rectangle looks like this. Okay. The reason this central rectangle is important is because the diagonals of the central rectangle form asymptotes for our hyperbola to follow. So that is the main reason that our central rectangle is important, because hyperbolas have these asymptotes as well. All right, so let's take a look at our equation in general form for a hyperbola. Our equation in general form looks very similar to our equation of ellipses, where we have x squared and then fractions y squared over something equals 1. The only difference is that we have subtraction between our two fractions. X squared over a squared minus y squared over b squared equals 1. Or we could have our fractions written in the opposite order, where we have y squared minus the x squared equals 1. Very similar meaning. For both of these cases, the vertices are at plus or minus a. Okay, so the nice thing about hyperbolas, the vertex always comes first, whether it's x first or y first. The vertices are always first, where we didn't have that, that same reliance with ellipses. Okay, the main difference is that if x squared comes before the y squared, that tells us our hyperbola is horizontal, and that our hyperbola has this shape, where if the y squared comes first, that tells us our hyperbola is vertical. But again, either way, those vertices can be figured out by whatever a is. Now, what does b mean? B is important because it tells us the other length of the central rectangle. So if I draw a quick little sketch here of what our hyperbola might look like, let's imagine I have a horizontal hyperbola. Okay, A again is going to tell us where our vertices are. So our vertex happens at A. B tells us this other dimension of our central rectangle. So B is up here. And just like before, ellipses, when we had foci, we have foci with hyperbolas as well. Our foci are inside our hyperbola. So we would have a focus here. And we would have a focus here. So we're actually going to be able to do a very similar process with our right triangles to figure out where the focus is in a hyperbola, where we have this little right triangle here. Use a different color. Okay. If you imagine, here's your right triangle. This length is A, this length is B, this length would be C. That is going to tell us where our focus is. And we will see that in example 1 in just a second. But that is our general form for equations of hyperbolas.